Hi, in this video we're going to take a look at cycloalkanes and the fact that some of the cycloalkanes, depending on their structure, can exist as what are called cis or trans isomers. So if we were to take a look at a very simple cycloalkane, let's look at 1,2-dimethylcyclopentane. This molecule, it turns out, can exist in two possible orientations. Now, in this type of drawing, it's kind of hard to see that, but I'm going to draw it in a slightly different way that will help illustrate the fact that this can exist as two isomers. Now, just for argument's sake here, let's just put in the two extra hydrogens that would each be at carbons 1 and 2. And let me just number the carbons 1, 2, 3, 4, 5. That's an arbitrary, I could have gone the other direction. The key is both of the carbons with the methyl groups coming off would have to be either numbered 1 or 2. So what I'm going to do is I'm going to sort of tilt this molecule so that it's more facing you and draw it in a more three-dimensional way. So to do that, let's envision turning our ring sort of on the side. And let me darken in these bonds here in the front. So this is carbon 1, 2, 3, 4, and 5. And let's take a look at the methyl groups now. There's actually two possible orientations that I could have this. The first one I'm going to draw, let's say that we have both methyl groups on the same plane, or I'm sorry, on the same face of the plane defined by this ring. So in this case, both of the hydrogens coming off carbons 1 and 2 would both be sticking above the plane. So notice in this that the two methyl groups, the two CH3s, are on the same face of the ring. So in this case, when the two methyls are on the same side, that equals cis. Okay, so that little word cis means that they're going to be on the same side or face defined by the ring. Conversely, let's draw the other possible structure here. Again, I'm trying to draw this sort of three-dimensionally, and I'll darken in these bonds here in the front. This would be carbon 1, 2, 3, 4, and 5. Let's draw the opposite isomer, where I keep one of the methyl groups sort of in a downward direction relative to the plane, but the other one's going to be sticking up. So I've just basically flip-flopped the hydrogen and the methyl group back on carbon 2. And what that does, it also flips the hydrogens. So now I have a hydrogen coming off carbon 1 that's sort of sticking up relative to the plane defined by the ring. Off carbon 2, the hydrogen sticking down. In this case now, the two methyl groups are in a trans orientation. So different or opposite sides equals trans. Now, both of these molecules are clearly the same molecule. They're 1,2-dimethylcyclopentane. However, because of the different orientation of the two methyl groups, the different connectivity, these are considered to be isomers. So the first one here would be named as cis 1,2-dimethylcyclopentane. So notice I put the little word cis in front of that. As you might expect, this one here is going to be named exactly the same, except I'm going to replace cis with trans. So this would be just listed as trans 1,2-dimethylcyclopentane. So cycloalkanes, if they have multiple substituents on them, can potentially exist in the cis-trans isomers. In the next example, we're going to take a look at a slightly different way to draw these in a little bit more simplistic way. All right, so continuing on with our example, we just were looking at the 1,2-dimethylcyclopentane. Rather than drawing these out in sort of the flattened ring, sort of the real three-dimensional look to them, let me just show you how you could draw these in a more simplistic way, just using either dashes or wedges. So with this molecule, I could draw the cis orientation like this. Okay, so notice I've used two wedged bonds. Both methyl groups would be sort of going back into the plane. They'd both be on the same face of the ring. I could have also drawn this molecule where I use two wedges, where the two methyl groups now would be coming out. And I've basically indicated that these are in fact the same molecule. If you built a model of this and just simply flipped it over 180 degrees, you could see that the methyl groups would in fact align. So both of these, where we have two either dashes or two wedges, these are going to be the cis version of this molecule, 1,2-dimethyl cyclopentane. Now the trans molecule, as you might expect, we're just going to flip one of these dashes or wedges. So in the first case, let me keep my methyl group here as a dash, but now on this one, I'm going to put a wedge. That's indicating that two methyl groups are now on opposite faces, so this is going to be the trans 1,2-dimethyl cyclopentane. Now, I will draw the other isomer of these, where I now make the methyl group up and this one down. Now you might think these are in fact identical. They actually are not. This is a more advanced topic dealing with stereochemistry. If you actually flip this over, you'll see that this methyl group does not line up with this one. These two are definitely isomers of each other. They're both going to be considered trans 1,2-dimethyl cyclopentane, but we're going to save the actual stereochemistry question of these for a later topic. So I hope that helps a little bit with cis-trans cycloalkanes. We'll take a look at one more example here. All right, we'll do one more example to look at cis-trans isomers of cycloalkanes. And let's just, I'm going to draw a structure and let's go through the naming process. So let's take a look at this molecule and see if we could name this now. Again, first thing to do is name it just like you normally would a cycloalkane, but you want to be recognizing that some of these bonds are actually showing some directionality to them. So first off, we have to decide how we're going to name and number the ring. Well, here we have an ethyl substituent, CH2, CH3, and here we have a methyl. Ethyl comes before methyl, so we would number this one 1, 2, 3, 4, 5, and 6. So the name is going to be 1-ethyl, and then we have a 3-methyl, cyclo, don't forget the cyclo, I have a 6-membered ring, hexane. Now we have to determine, okay, what is the orientation of those two groups? Well, clearly this group, the ethyl, is sticking out. This one's going back behind the plane, so these are on opposite faces defined by the plane of the ring. So this is going to be a trans orientation. So we would just put the little word trans. If this were flipped to be, say, a wedge and both were sticking out, that would be the cis example. So get a little bit more practice taking a look at these. They can be a little bit tricky. Good luck.